Hey curious minds, welcome back to MindSpark, Science Now. Today we're talking about a medical first that pushes CRISPR technology from the lab straight into a neonatal intensive care unit. This is the story of baby KJ, the very first person to receive a fully personalized in vivo gene editing treatment, and how that single case may open the door to made-to-order cures for thousands of ultra-rare diseases. A race against ammonia. KJ was born at the Children's Hospital of Philadelphia in August 2024, looking healthy. But within days, doctors found dangerously high ammonia in his blood. The cause was severe carbamoyl-phosphate-synthetase 1 deficiency, or CPS1 deficiency. It's an ultra-rare urea-cycle disorder that prevents the liver from detoxifying ammonia. Without rapid intervention, the toxin can cause seizures, brain damage, or death. Conventional management is a strict low-protein diet, heavy medication, and if the child survives long enough, a liver transplant after the first birthday. For most babies with the severest form, time simply runs out. 2 typos in KJ's DNA. Genetic sequencing revealed that each of KJ's CPS1 genes carried a nonsense mutation, one called Q335X from his father and another, E714X from his mother. Both mutations insert an early stop signal that halts production of the detox enzyme. Fixing even one of those stops could give KJ's liver enough working enzyme to control ammonia. Choosing the editing tool. Instead of the classic CRISPR-Cas9 scissors, the team at Chop and Pen Medicine chose adenine base editing, a molecular pencil that swaps a single DNA letter without cutting the double helix. The editor they built converts an A to a G, turning the Q335X stop code N back into a working amino acid code. Mistakes are less likely and the repair is permanent in any cell that gets the edit. A delivery truck made of fat bubbles. The editing machinery messenger RNA for the editor plus a custom guide RNA nicknamed Kajigaran was packaged inside lipid nanoparticles. These microscopic fat spheres naturally home to liver cells, making them ideal for a disorder whose root cause sits in the liver. 6 months from idea to drug. From the day KJ received his genetic diagnosis to the day the first clinical grade batch was finished. Just 6 months had passed, about 3 times faster than typical gene therapy timelines. Toxicity tests in mice, manufacturing under good manufacturing practice standards, and an emergency use submission to the US FDA all happened on an accelerated clock because KJ's life depended on it. 3 infusions, 1 remarkable turnaround. On February 25, 2025, when KJ was a little over 6 months old, doctors infused the first low dose. 2 higher doses followed in March and April. Ammonia levels fell instead of spiking. And within weeks, KJ could tolerate more protein, required fewer scavenger drugs, and began hitting motor milestones, like sitting unaided and waving at his parents. Heading home? 307 days in total. After spending his entire life in hospital, 307 days in total. KJ was discharged on June 3, 2025. He left the building smiling in his stroller, flanked by his overjoyed family in a hallway full of cheering nurses. He'll return for quarterly metabolic checks and yearly liver biopsies. But so far, there are no serious side effects and no signs of liver inflammation. Why this matters beyond one child. What makes this case revolutionary isn't only that it saved KJ, it's the platform behind it. The same lipid shell, the same mRNA backbone, and the same safety pipeline can, in principle, be reused. Swap in a new 20-letter guide RNA, and you have the blueprint for the next patient's therapy. Researchers are already adapting the system for other urea-cycle disorders, and for conditions like Artemis's CID. Tough questions we can't ignore. Personalized cures raise thorny issues. Who pays for a therapy built for a single patient? Will families with resources jump the queue? And how many N-of-1 cases equal enough evidence for regulators? Advocates argue that scaling the platform will drive prices down much as mass production did for mRNA vaccines. But transparency and global collaboration will be essential to avoid genetic privilege. The new horizon. KJ's story shows that a fatal mutation caught at birth no longer has to be a life sentence. Gene editing is moving from population-scale treatments to person-scale surgery, performed in real time against a ticking clock. If this platform proves durable and affordable, the next generation of babies born with ultra-rare errors in their DNA may have a fighting chance from day one. Stay curious, hit subscribe, and let us know in the comments what other frontier breakthroughs you'd like us to explore. You've been watching MindSpark. Science now where discovery meets urgency. See you in the next video.